Log on, tune in, find out. Another good idea from Cambridge.
Yeah, thank you. I'd like to thank the organizers for inviting me to speak here. So this lecture is about moduli spaces and physics. So what I'll try to do is to outline, to sketch some string theoretic perspective on cohomological and enumerative aspects of moduli of sheaves on Calabi-Yau threefold. Okay, so that's kind of the goal. Since it's only one lecture, it will not be very detailed, but rather I will just concentrate on outlining the main aspects. So let X be a smooth projective Calabi-Yau threefold over C. Everything is over C in this lecture. Or, I mean, most of the time I'm going to talk about this case, but I should say that a lot of this stuff goes through, and it applies to the so-called local case, in which it's a smooth quasi-projective Calabi-Yau threefold over C, and it's equipped with a torus action, algebraic torus action, such that the fixed locus is projective. But to be concrete, I'm just going to talk about this most of the time, and then some I'm going to maybe mention a few things of what happens in the local case. So this is the so-called local situation. Okay, and okay, also to simplify things, let's assume that the cohomology of X is torsion free. So it's a free Z module. All right, so now let's take J to be a, say, a Kähler class on X. And J, it's known that J determines a stability condition. I mean, determines actually a few stability conditions on the abelian category of coherent sheaves on X. And that has been explained in detail in the previous lectures. You have a condition defined by Giesecker stability, which is a polynomial stability condition, and you also have some sort of a truncation, the slope stability. So I'm going to call, let's call mu Jf the slope of some coherent sheaf X, F on X. And I'm going to pretty much talk about this because this is somehow appears more naturally in physics. And in fact, more generally, what you would like to do, is to pick some element, I don't know, let's call it tau or something, in the space of Bridgeland stability conditions. So this is the space of Bridgeland stability conditions on the derived category dB of X, and then study properties of moduli spaces of stable objects in the derived category. But this is really very much work in progress in mathematics, and I'm not going to say, well, I'm going to say a few things about that, but not too much. Okay, so now let lambda X be the Grothendieck group of X, quotiented by numerical equivalence. So we divide by numerical equivalence, and there is a Chern character map from lambda X to the even rational cohomology of X that I'm going to have to use. So let me start with a few known facts. So in order to set discussion on firmer ground, so let me list a certain, well, it's part of it is rigorous results. So let's list some mathematical facts. I will try to make a distinction between theorems and conjectures, although it's hard for a physicist to do that. so so let me just mention a few facts. So there is, first of all, there is a algebraic moduli stack. I'm going to call M SSJX alpha of slope semi-stable coherent sheaves on X, which is known to be a finite type. Okay, so there is that, and then you have an open substack parameterizing stable objects, just to set the ground for discussion. So you have an open substack parameterizing, then you have MS in here. This is some open substack parameterizing stable, so mu J stable object. Okay, and now what's also known is that suppose if, in many examples, suppose that stability, so slope stability, is the same as slope semi-stability, which means to say that there are no strictly semi-stable objects. So if this is satisfied, then there exists a projective coarse moduli space. I'm going to call MS JX alpha of stable objects. Okay, so now by work of, so it's all in physics, it's most of what I want to say, it's about numbers. And in order to get numbers out of moduli spaces, we have this machinery of virtual fundamental cycles. So now there is not the result of Richard Thomas. What he proved is that in this case, so no, in our case it's MS, the moduli space of stable objects has a perfect abstraction theory. So so there exists a virtual fundamental cycle, which is an algebraic cycle of degree 0. So it lives in the 0 degree part of the Chow group of the moduli space. And this 0 here is just the expected dimension of the moduli space. So of course the moduli space itself, it's a pretty ugly scheme. We have components of the wrong dimension and non-reduced components and whatever have you, but okay. But you have a cycle that lives in here, and then you get a virtual number of so if this condition is satisfied, so if MS is in fact projective, then you get a virtual number of sheaves, which I'm going to call DT, which stands for Donaldson-Thomas invariant. Donaldson-Thomas invariant JX alpha, which is just the push forward of the function 1 on the push forward of the cycle down to the point. So or the integral of 1 on the virtual cycle, and it's an integer. It may be negative, but it's an integer, so that's the virtual number of coherent sheaves in class alpha, stable coherent sheaves in class alpha. Okay, so that's one thing, and now there is a generalization of this story, which is due to Kontsevich and Soiberman and Joyce and Song. So there is a more a generalization of this. Now I have to be careful. It's already, you have to start branching off between theorems and conjectures. So now, so what was proven effectively by Joyce and Song, that even if that condition is not satisfied, so if there are strictly semi-stable objects, so even if S is strictly there are strictly semi-stable objects, then you can still define some generalized Donaldson-Thomas invariants, which this time are rational. They are not integers, and their machinery for defining them is quite complicated. I can't possibly review it in one lecture. And there is also parallel work by Kontsevich and Soiberman, which work in much more generality, although part of this work is still conjectural, which applies to this case, so which still gives you some, you get some, in their case, you get some kind of integral invariant associated even into this situation when you have semi-stable objects. And then there is some, that's called down in the name of the multi-cover conjecture, which tells you how this invariant, the Ks invariants are related to the Js invariant. So the statement is that dt, the rational invariant, is given by a formula like this. It's a sum over all integers k which divide alpha, k greater or equal to 1 over k squared dt bar j x alpha over k. So they tell you how the two are related. Okay, so that's the story about Kontsevich and Soberman. It's partially conjectural from what I understand. My understanding is quite limited because it uses some motivic integration machinery that I don't know. It's partially conjectural, still partially conjectural, but it's supposed to work in much more generality. So it works for objects, moduli of objects in a triangulated category subject to some conditions.
I'm sorry, I think I got lost. What is alpha?
Alpha was the class of the shift. So alpha is whatever the class. Alpha is an element of the Grothendieck group of X modulo a numerical equivalence. It's basically it's the
What does it mean for k to divide alpha?
well, this is going to be a lattice, right? So it has an integral structure. This is a lattice. It's the Z module. So what I mean that k dividing alpha means that there exists an alpha prime in the same thing, so that alpha is k alpha prime. Okay, so that's the story that this was developed by mathematicians. It has physical motivation. And I should say that there is we are moving more and more towards conjectures. So there is a conjectural refinement, which I would like to say a few words about it. So we have a conjectural refinement. So this actually follows from this work of Kontsevich and Soberman on motivic Donaldson-Thomas invariants. So at least one piece of their part of their construction predicts the existence. So you should be able to find, again, for any alpha and j sufficiently generic, there exists some kind of polynomial refinement. So you should find some invariants I'm going to call dt bar jx alpha, which now take values. They are functions of some formal variable y, and they are log polynomials in y with integer coefficients. And so they are called a refinement because once you evaluate this at y, you get the numerical invariants defined before. So at 1 is just a numerical invariant defined before. So that's one thing. And then there are a few properties of these invariants. If you expand it, if you write it as a polynomial in y and y inverse, then dk, minus y to dk, then the coefficients have to be positive or 0, and dk equals b minus k. So there are some special properties of these invariants. Okay, so in some sense, you can think of very loosely, very loosely, I would say, this is some kind of Euler characteristic of the moduli space, although it's defined with respect to a special constructible function, Behrens constructible function. And this would be somehow some kind of virtual polynomial of the moduli space, but this is very loosely. So virtual Poincare polynomial. But I would not. I'm not saying this is an accurate description. So anyway, Kontsevich and Soberman by their motivic theory tell us that something like that has to exist.
Is the kind of potential function?
A what?
Potential?
Virtual Poincare polynomial, a potential.
Yeah, I mean this dt bar of y.
A potential for what?
Some physical theory.
Oh, I wouldn't take it like that. No, you mean y to identify y with the physical field?
Yeah.
No, I wouldn't. No, I wouldn't do that. I mean, it's not natural from the physical point of view. I'm going to describe the physics right now, so I'm going to switch to physics in it. I just started with the math because sort of it's probably more familiar to the audience, and we should have some firm ground behind us before we start talking about the physics. So basically, what's the goal well, both for mathematicians and physicists, I guess, is to try to understand properties of these invariants, how to compute them, I mean, make generating functionals and try to study their properties and so on. A lot of work has gone into deriving wall-crossing formulas. So what happens when you start varying J? But I'm not going to talk about that because it really requires a lot of machinery. So what I wanted to do next is kind of try to explain how a physicist would think about this, and then extract some general statements concerning properties of these invariants. Okay, so let me just try to outline what the physics point of view is, which is going to be probably harder to explain because, well, I mean, things are not really defined in physics. Things are just there. So, well, okay, so let me just say a few words just to try to give you a feeling for what's happening. So the physical interpretation, or better say string theory. So if you're given a Calabi-Yau threefold as we are given here, we take a product with, for example, with R4, we construct a 10 manifold, and this defines what's called in the physics literature as a type 2A string vacuum, supersymmetric string vacuum, supersymmetric vacuum. And then well, this is actually equipped with a metric of signature minus plus plus plus. So it's not the Euclidean metric; it's the Minkowski, the so-called Minkowski metric. And then you have here of course, you have the theory has the symmetry, which is the spin group of signature 1, 3, and this contains inside spin 3 embedded in a canonical fashion, which is in fact SU2. So this is a symmetry group. So physics kind of you add dimensions and you got a bigger theory. And now what the physics prediction is that in this theory there should be the so-called Hilbert space of BPS states. So remember this lambda of x, which was this. So what are, first of all, let's say what are BPS states? This is not a definition, as I said, but to just give an idea, they're just quantum states of massive supersymmetric particles in the four-dimensional effective theory. So probably these words don't make much sense for mathematicians, but this is what what physicists will tell you. More concretely, you say there has to be a Hilbert space of such states because they are quantum states. So quantum mechanics means the particles are really wave functions in the Hilbert space. So there is some Hilbert space which depends on J and depends on X, and it's graded by elements of lambda of X. So you have some graded pieces for each alpha. So by the way, for a physicist, this alpha here is called a charge vector. So you have graded pieces like that. And because this is a symmetry of the theory, then you know that this SU2 has to act on each graded piece. So there is an action of SU2, which means that each graded piece, and it's compatible with the inner product, so each graded piece has to decompose as the sum of irreducible representations of SU2. Right? So if you choose, let's choose a maximal torus inside, and you identify the weight lattice of SU2 with Z, then you can further write this Hilbert space as the sum over as a sum over. You can refine the grading by adding. So you can write HGPS J of x. It's a sum over alpha in lambda, sum over some L in Z, and you have let's see how to write it in a careful way. So so this is really what this block is. It says that SU2 acts here. It's a sum. It's a finite sum of so this is a finite sum of the irreducible representation of SU2 labeled by L, of highest weight. So this is the irreducible SU2 representation labeled by with highest weight L. Okay, so that's kind of a very general statement. This comes just because the symmetry is there, so it's very robust. In other words, it doesn't care. So far, I haven't explained what's the connection between these Hilbert spaces and geometry. But it doesn't, when I say it's extremely robust, it doesn't care if you think about sheaves or derived objects on X, or it's very, very robust. It's very general. And then you define what's called the BPS index. The BPS index, let's call it N, J, X, alpha. It's just the trace. So I said I was choosing this, so let's call H the generator of the Cartan generator. So it sits in the Lie algebra, in the SU2 Lie algebra. So it's trace on what? Trace of on this X alpha of -1 to the H. That's an integer. That's an integer. And then you define a refined index. Now I have to put index in quotation marks, because one thing I haven't discussed in detail is whether this is independent on deformations of X, for example. And this is known to be independent, but the refined one, it's not known to be completely independent of deformations. So you just define it, Nj, it's a Rogern polynomial of Y. It's a trace of in the same piece graded by alpha, but now we trace -y to the H. So this is going to come out something in Rogern polynomial in Y. Okay, so that's the story that the physicists will tell you without any reference to the geometry of X. So X became a black box. The physical sort of intuition is that you take a limit in which the volume of S is extremely small, and because this is a non-compact manifold, then all the physics you see is physics on this non-compact part. So that's why it's called an effective theory. So then you have this Hilbert spaces, and everything follows from symmetry and supersymmetry, which that's why it's extremely robust. So this one became a black box. But now let's go back and see what's inside here. So how do we relate this picture to geometry? No, I can't say. That's the problem. That's what I'm trying to say now, at least in a conjectural way. In physics, there is no way what you would like to have, ideally, that's what I'm trying to say. Ideally, what you'd like to have a definition of the Hilbert space in terms of X. Well, I don't have it. I mean, nobody has it. But I'll try to say what it should be instead of what it is. And in some examples, it's actually mathematically rigorously constructed. But let me say, so now the geometric interpretation. Hopefully it's going to become actually, maybe I should call this maybe a physicist wish list. What would happen ideally? I'm not even a conjecture, because I don't think it's really a well-formulated conjecture. But what should happen is the following: that if you're for any alpha in this lattice, and J sufficiently generic at least, let's stay away from very special behavior. There should exist a cohomology theory, let's call it HBPS, of the moduli stack of let's say slope semi-stable coherent sheaves with invariant alpha. So this is some kind of cohomology theory, which hasn't been constructed. In some special cases, I'm going to say it's known what it is, but in general, it's not known what it is. There's going to be some kind of cohomology theory. So, and then simply these Hilbert spaces. Well, I mean, let me just forget the word Hilbert here. Let's forget the inner product structure. But at least if you forget the inner product, because I don't want to talk about that, that's even more complicated. Then these spaces that I have there, H, J, X alpha, should be simply this cohomology of the moduli stack. And because we saw here there is an SU2 action here, the only reason it was, this is a complex space, so the only reason it was SU2 is because you wanted to be something compatible with the inner product. But if we forget the inner product, then there is nothing to stop us from complexifying it. So there's going to be an SL2C action here, which is nothing else but some kind of Lefschetz action. Should be, I should say. This is a Lefschetz action. So in other words, if this space happens to be a smooth variety, then this is the Lefschetz action, and cohomology is just the usual cohomology, whichever way you want to describe it. But the really interesting question is when this moduli space is not a smooth variety or a normal variety or something like that. It's really a complicated stack. Okay, so that's the hope. And then, of course, under this, what you would like to have is that this n BPS, this BPS index is identified with the Donaldson-Thomas invariant, the integral one. So this has to be some kind of Euler characteristic of the cohomology theory. We don't know. If everything is done right, this is what has to happen, and then the refined ones would be some kind of Poincare polynomial. So if I define this is going to be some kind of Poincare polynomial of the same thing. As I'm saying, I'm stressing we don't know how to do this, but that's, from a physicist's point of view, the way physicists think about these states, this is what should happen. And in many examples it does, but there is no general theory, so that's the problem. There are many situations you can think about. So for example, suppose you had a family of, suppose you look at deformations of X, and suppose you had a family of moduli spaces which deform with X. And suppose all these guys are, for generic points in the parameter space, so suppose they are smooth varieties, so then you know what this is. But then there are special points when the moduli space develops something like a non-reduced component or something like that. Then you stop knowing what this is. And this is the kind of question that I don't think it's known how to answer. Okay, so but now, okay, so what I want to do is to say, well, let's accept this. Or, well, let's say, well, we don't know what to do, but let's see what we can learn about these invariants, which are well defined, from physics. What physics tells us about these invariants. So there is a story in physics that's called the M-theory lift, which is a very powerful way to derive new results. So it's something called the M-theory lift. So what I'm trying to explain is that even if you don't know what this is, you can still use this conjectural, not even conjectural, this kind of heuristic picture to derive interesting properties of invariants that are understood, that invariants that are well defined. Okay, so what the observation is the following, is that in fact there exists a one parameter family of M-theory vacua. Okay, this is some physics terminology which is simply you have M-theory compactified on an 11 manifold of this form, and this is just a circle of radius r. R is the parameter in the family, so it's a real family. R is, of course, so now the type 2A vacuum that we had before is just a specialization at r equals 0. So there's a construction. It's in physics that tells you that in fact you have a family of theories of vacua, which is parameterized by, in this case, by just one parameter, and the type 2A vacuum we had before is just this. It is obtained in this limit. However, what you can do, you can also take R, so you can take the opposite limit, in which you really try to decompactify the circle, make it extremely big, so in the end, in this limit, you're going to have M theory on X cross R5, the so-called 5-dimensional limit. And there is another kind of arguments, circle of arguments in physics that tell you that these Hilbert spaces have to be preserved. So there's got to be not just a family of theories, but the BPS Hilbert spaces would be somehow, there's a family of BPS Hilbert spaces. Whatever. I have to stick an R in here. And there's a family of them, and actually many of their properties are preserved. So you can study, in other words, you can learn new things about properties of the moduli space at R equals 0 by studying the moduli space at R equal infinity, if you want. So that's the kind of philosophy that is can give you new results. So let's see what we learn by this. Now, what you learn is very sensitive to alpha, right? What you learn, it depends very much on what kind of numerical invariant you have. So I'm going to have to go on a case-by-case basis. So so let's take the first case I want to discuss. I'm not going to be exhaustive in this analysis, but the first case I wanted to discuss, suppose, this first case is the so-called Gopal-Kumar, was considered by Gopal-Kumar and Vapa. So suppose alpha, turn 0 of alpha is 0, turn 1 of alpha is 0, turn 2 of alpha is minus beta with some curve class. It's a curve class, also called a curve class. And then, well, let's say chi, the holomorphic Euler character, is just some integer n. Okay, so you look at this moduli spaces. So really, these are moduli spaces of pure dimension 1 sheaves, so subject to a slope stability condition, because I killed the first two components. So it's, roughly speaking, sheaves supported on curves. Okay, so what you learn in this case, by taking this limit, what you learn is that it's very robust. It comes only from symmetry arguments. Here, again, I have a metric with signature, minus plus plus plus. So there is a symmetry group which is spin 1, 4. Okay, it's spin 1, 4, and actually this contains a spin 4 subgroup, the one that fixes the time direction. And this is isomorphic to SU2 cross SU2. And moreover, because I fix these invariants like that, I know that massive supersymmetric particles in type 2A have to lift to massive supersymmetric particles in M theory. But if that's true, then what this predicts about this picture is that in this particular case, you have to have a refinement of the Lefschetz action. So the prediction here is that there's going to be a refinement of this Lefschetz action on the cohomology. So let me describe that in some detail. This is how Gopal-Kumar-Vapa invariants are defined in, well, not defined, but whatever. They are, well, yeah, defined in physics. Well, okay, so what you have, so now you're predicting that there has to be this cohomology theory carries now a double SL2 action. So let's give them some names, I don't know, 1 and 2, left and right, plus, minus, whatever have you. And the old one is just the diagonal subgroup. So the one that was there in type 2A, let's give in type 2A here, it's a diagonal here. And this is what happened in M theory. So it's already telling you now, SL2 is kind of generic, at least if you know, if you have this is a smooth variety, then you know that there is an SL2 action by Lefschetz. Now here, you learn that there has to be some refinement. So the moduli space will, so now if you take this graded piece of the cohomology, so this one has to be now a sum over two integers. So you can define, and then you have some multiplicities. Let's call them n, x, beta n, L1, L2. So these are positive integers. And then you have the irreducible representation L1, L2 of SL2. Well, what I just mean is this vector space n copies, but it's easier to write it like this. Okay, so you get this invariance. So these are the refined GV invariants. And before I go any further, I should say that, as I said, in certain special cases, this picture actually has a very nice geometric interpretation. So there is work of, let's mention this. I mean, there is work of I think it was Hosono, Saito, Takahashi. So if you assume that the moduli space, or so let's assume first of all that stability and semi-stability are the same. I don't want truly semi-stable objects. So then I have, let's assume that the moduli space of stable objects is a variety. Maybe I need normal. I'm not quite sure. Maybe somebody in the audience can tell me if I need normal or not. But in general, it's a variety, and then you can identify this DPS cohomology theory with the intersection cohomology of this moduli space. And moreover, you have a structure that assigns, there is some kind of hitching vibration structure on this. So intuitively, the way you want to think about is that maybe a generic point in this moduli space is just a smooth curve in X with a line bundle on it. Right? So then you can understand, so if you're at the generic point, it's just a curve, a smooth curve here, and the line bundle L is a line bundle on C, and F is just I lowest log of L. So if you have points like that, you understand where the vibration structure would come from. This is just an intuitive explanation. It's fiber, so you can map this to the support, and then you have a vibration by the Picard group of C. So in other words, what you can argue is that there is some kind of Hitchin map, Hitchin-like map, I should say. It's not. I'm not a map to some base. And then this double SL2 action follows from the decomposition theorem for this map. So you have it's a Hodge theoretic statement.
Excuse me, what is that? Is that usual cohomology? What is that?
The intersection cohomology.
The HBPS on the right?
Well, if it's smooth, then it's usual cohomology. But if you work about singularities, then you have to work with intersection cohomology. Not. And anyway, so the decomposition theorem gives you some this SL2 action. So in this particular case, in these cases, you do have a mathematical construction of what this is supposed to be and how you get everything. And then these numbers that appear here are very well defined. You just have to look at the SL2. You have to break the cohomology in representations and count the multiplicities. So this can be done in special cases, but not in general. We don't know how to do this in general. Well, here you have two, because roughly speaking, you have very roughly, because a Keller-form pullback from the base and then a relative ample class. So you get two actions that way. But it's very technical, because you really have the construction is explained by in that paper. You have to use the Lorentz spectral sequence for intersection cohomology. So
What is B here?
what's B?
Base.
What is B? Naively, I would say it has to be a component of the Hilbert scheme of curves. You map by support. You have a coherent sheaf. You map by the scheme theoretic support. That would be, at least in the cases that this works. I mean, that's how you do it. Okay. Now, let's step one step further. So now what can we learn by looking at different vectors, I mean charge vectors, alpha? Well, you can learn something else by playing with that. So the same game can be played with other charge vectors. So what happens? So the second case I want to look at, it's really a case. Actually, this time I'm not very consistent here, I know, but it's really, I'm going to go outside. So let's take invariants like this. This is a curve class. And then I want M to be the holomorphic Euler character of alpha. Well, what is this -1? Well, obviously, because I have -1 there, I'm not talking about coherent sheaves. I'm really talking about some kind of derived object. So what I want to think about, without getting into too much details, what I want to think about is this stable pairs defined by Panhari-Pandey and Thomas. I should have probably said in the beginning, there is one very important case in which we understand very well a moduli space of objects in the derived category, and this is this particular case, the moduli space of stable pairs constructed by Panhari-Pandey and Thomas. So you have the stable pairs are two-term complexes of this form, in which F is a coherent sheaf on X of pure dimension 1, and this is a section, and the co-kernel of S is 0-dimensional. It's a 0-dimensional sheaf. So that's really the stability condition here. I mean, these two conditions are in. Okay, so these are actually going outside the coherent sheaves. These are really objects in the derived category. And you can, what they showed is that they proved is that you can construct the whole machinery. You have a perfect obstruction theory, you have virtual cycles, and the moduli space is projective. It's a projective scheme. So you have virtual numbers of stable pairs. So the result is a theorem of Panhari-Pandey and Thomas saying that there is a projective moduli space, a projective moduli space with perfect obstruction theory. So you can define some virtual numbers, of stable pairs using the virtual cycle. Okay, so now what we learn about these numbers using this M theory construction, that's the question I want to answer. So I wanted to leave, I erased that. Okay, what we learn is the following. So this was analyzed by Dijkgraaf, Waffa, and Verlinde. There's a Verlinde, what they showed is that physically what happens when you crank up the radius to infinity, what happens, you get massive particles, massive supersymmetric particles. But they live not in, remember, first I said that the manifold was R4, but in some kind of in a hyperkähler 4 manifold times R. So what happens in this case, you change the geometry of your space-time. So this is a hyperkähler 4 manifold times R. It's actually, in this case, it happens to be isomorphic to R4 as the topological space, but the metric is a different hyperkähler metric. And by analyzing the physics of this system of particles, they predicted the following conjecture, which is nothing else but, this is sometimes it's the physical interpretation of this thing that's called the strong rationality conjecture of Panhari-Pandey and Thomas, but in a refined form. You can even get it in a refined form. So let me just spell it out. So let me spell out what you really get. What you get is the following. So suppose now you make a generating functional. It's a generating function which I want to sum over all curve classes and all integers. So I'm going to have a multi-index, let's go capital T to the beta, Q to the n, and then I have pt x beta n. And I can look at the refined form. In the strongest form would be a function of, so this would be a function of t, q, and some y. So suppose these are the refined invariant. And then you refine what I said, what it was in the beginning. It's this thing that comes out of Kontsevich-Soibelman theory, which says that there has to be a virtual Poincare polynomial that refines the virtual Euler character. I mentioned that in the beginning, but probably I went too fast. Probably. Yeah. So the theory of motivic Donaldson-Thomas invariance of Kontsevich and Soibelman, although it's conjectural, still conjectural, not completely, the foundations haven't been worked out, predicts the existence of this polynomial invariant. So these guys live in, they are Laurent polynomials in Y. Okay, so what you learn about, so the question is, what does physics predict about this generating functional? Well, what it says is the following. It's a funny thing, so, but okay. So it says that this generating functional has to be the exponential of something I'm going to call some Gopal-Kumar-Vafa function, of x, which also which depends on, well, the same variables, pqy. So let me see what that is. Let me just write down what that is. It's a function that looks like this. It's a generating functional for the Gopal-Kumar-Vafa invariant. Just write it down. It's slightly complicated. So. Okay, so this is refined. Let's refine this one too. So let's refine. Okay. T, Q, and Y, something of the following form: k greater or equal to 1, sum over beta in H2, not 0, and then sum over these two weights of the SL2 times SL2 action. Then you have t to the k beta over k minus 1 to the L1 plus L2. Okay, I'm going to say these are the refined Gopal-Kumar-Vafa invariants. Okay, so this is how this function is defined. This is just the trace. The H1 and H2 are the generators of the Cartan of the two SL2 factors. These are the refined Gopal-Kumar-Vafa invariant, refined GV invariant. But there is an element of, in order to be precise, remember before when I defined these, I defined them purely in terms of defined, quote unquote defined. When I spoke about these invariants, they were associated to this BPS cohomology on the moduli space of stable sheaves of pure dimension 1. And in that case, you had dependence on the degree. So there is a further conjecture hidden in there that these invariants are actually independent of degree. So remember, recall that these guys were, so you took these BPS states. So it's a very, I want to insist on this point because it's an interesting connection, right? So we had a moduli space here, a slope semi-stable dimension 1 sheets. So these are slope semi-stable Fs, right? With churn 0 equals 0, churn 1 equals 0, churn 2 equals F is minus beta, and so on. So these numbers were manufactured out of the cohomology of this space. And then you had this SL2C squared action in here. And you counted multiplicities of irreducible representations. Now, what I want to point out that there is an n in here. You have to specify n is the Euler character of F. Well, there is a conjecture hidden in here is that says that these numbers are actually independent of n. That's why I didn't write n there. So you had, this was broken in some direct sum of some n, I wrote it beta n L1, L2, R L1, L2. So the conjecture is that these n's, that we don't know how to define anyway, are in fact independent of n. And another interesting aspect of this is that you have two different moduli spaces involved here. On this side of the equality, I'm counting stable pairs. Maybe in a refined sense, whatever. But I'm counting. This is manufactured out of moduli virtual numbers of stable pairs. Now this is manufactured out of the cohomology. This cohomology I can define of this moduli space of pure dimension 1 sheets, which are slope stable, semi-stable. So then this equality kind of relates them. It ties them together. So that's kind of it's a non-trivial aspect of the whole story. And this was formulated in the paper by Pandaripandi and Thomas. This is, in a slightly different form, this is the strong rationality conjecture, their strong rationality conjecture. But what I wanted to insist on is that these numbers here are really numbers of some kind of numbers of irreducible blocks in this cohomology space. And in fact, in situations when this moduli space is actually nice, like a smooth variety, this actually gives you very highly non-trivial connections between these two moduli spaces, because in that case, cohomology is well-defined. These numbers are well-defined. And you can ask yourself if there is a intrinsic geometric understanding for this kind of relation. So I would like to formulate this question. I mean, at least in situations when the moduli space is good, and we know what we mean by this cohomology theory. So if this moduli space there is nice, it's a smooth variety, for example. Is there a geometric understanding of this relation? I mean, there is I'm not going to talk about it, I don't have time, but there is I say a nice example, a nice local example where this is very interesting. I mean, if you study this in a local case, in a specific local example, you get a string theoretic, whatever understanding, string theory framework for the work of Hausel and Rodriguez Viegas on the cohomology of the Hitchin system. So there are examples when this can be made quite concrete, and you can actually relate to other things, to things that are kind of traditionally studied independently of this. Okay, so I have 5 minutes left, and I don't think I can say much more. I just wanted to mention briefly one. I'm not going to get into details, but I want to mention one other case. And this other case is what happens when we look at divisors. So far I looked at curves, I looked at stable pairs. But what happens if you look at divisors? So I take 0, C1 of alpha. I want to be an ample, very ample divisor class, and so on. We'll have to fix the other ones because I don't have time to get into details. Well, actually, not necessarily very ample. Let me just. Well, okay. Let me just erase this. It doesn't have to be very ample. it's a divisor class, effective divisor class, maybe I should say. So what you learn by playing the same game, well, you learn that you can manufacture, you can take some kind of generating functional of, if you sum here over Chern 2 and Chern 3, and you take the Donaldson-Thomas invariants for this thing, the integral ones, there is a way of weighting them by constructing some kind of weight, which is a function here depending on some complex number tau, in such a way that the whole thing here is modular. So this is some kind of story that perhaps hasn't been, it's not so familiar to mathematicians, but I think it's a very important case. It has been discussed in the physics literature, so there is a bunch of names I should mention in connection to this. It's quite many names. I think that there is papers by De Boer, Cheng, Digraph, and Manscott. And then we have Gaiolo, Strominger, In, and then Denef Moore. Just a few names, in which it's pointed out that you can manufacture modular or quasi-modular forms this way. I don't have time to get into any details, and this actually is, if D in X is some kind of rigid Fano surface, this kind of modularity is related to the work of Goethe on moduli spaces of sheaves on D on surfaces. It's related to the previous work on previous results of Goethe on moduli spaces of torsion-free sheaves on Fano surfaces. But you can take the opposite case. You can take the case when D is a very ample class, not rigid. This is in some sense it's local, because then you can deform the objects away from D. But this is, you can take the case when D is actually a very ample class, and then there is still a claim in the literature that this has to be a modular form. And it's actually quite intriguing. In this case, it's not so much investigated in the mathematics literature. I think it's a good point to stop.
Is there any comment or question?
How does this M theory limit that you take turn pairs into sheaves?
The key point is that, well, it's a black box for, it's part of this rules of dualities in M theory. So the point is that if you have, let's take the easiest case, if you take O of X, right, in the limit, in the type 2A limit, when R is 0. Just take the structure sheet, or maybe R copies of this. Okay, so now you ask yourself, now suppose X is simply connected and so on, so this is actually rigid, so there is no problem. So the moduli space is just the point. And then you ask yourself what happens here. Well, the story is that M theory works in such a way, which cannot be explained, that it turns this into something like X cross some kind of hyperkähler form manifold, which is the so-called ALE space, for gravitational instanton of charge R. So it's a very explicit hyperkähler form manifold. We can write down the metric very explicitly. But the bottom line is that you started with the sheaf on X, with the vector bundle on X, and then you turn it into some geometric variant. So there is no longer sheathing here. Everything is just manifolds, right? So now if this sheaf has lower charge, this has like, if it's a pair. Now if you look at pairs, then this guy is a pure dimension 1 sheaf. Now this guy is not. It's just turning into particles there. So that's the rough explanation. It can be really explained. It's one of the the magic of string duality. It's not.
So there exists this wall crossing between dt and pt, right?
Right.
Physics, what is it? What's the analog of that wall crossing between what and what? think one of them would be type 2A, right? The DT theory.
No, okay, that's actually not, this M theory lift, I think it's not involved there. You just look at variations of you just modify the complexified Keller form. You just study usual wall crossing. You don't have to take any M lift for that purpose. Just stay in this limit and you just move the complexified Keller class. And you have to study the moduli space in the right category. And then it's a much more conventional situation in that case.
And can you also say these high-rank invariants, why are they interesting in the physicist's point of view?
Well, I mean, certainly they are interesting. All of them are interesting because you want to know as much as you can about these Hilbert spaces that I started with. And very little is known for the ones with the higher, associated to higher rank invariants. And yeah, I should say that in fact the case that where all this fails, it tells you absolutely nothing. If you have like turn 0 of alpha is non-zero, or let's say greater or equal to 1, 2, and turn 1 of alpha is non-zero, you get something very, very ugly that doesn't really shed any light into anything. So it's a kind of funny situation when you go to higher rank sheaves on X, torsion-free sheaves on X, and you have a non-trivial turn 1. It's kind of, you don't learn anything basically. So it's actually interesting to understand the math because here, at least from this point of view, physics doesn't tell much.
So, what problems should be solved by mathematicians? Like, kind of more specifically for these conjectures to be seen true or false, approximately.
Well, I can't say that they should construct this cohomology theory because this is true that they should be done, but I don't know how. I mean, this is not really a well-formulated problem.
So the first question is actually a formulated problem, and then.
Well, I mean, yes, at this level, I mean, construct a cohomology theory. I don't think it's a good statement. It's a good problem. It's just, yeah, it's. What you mean? What concrete problems? More concrete problems? Well, there are more concrete problems certainly to be understood. I mean, depending on.
Say there are a lot of unfamiliar words here for, like, average mathematician, and how do we translate this physics context and how to make progress on this? I mean, what do physicists say should be done by mathematicians?
Well, I guess that would be the ideal, an ideal situation in which somebody actually constructed the cohomology theory. I mean, we really had a good cohomology machinery for all this. I mean, well, I mean, there are many. I can come up with smaller problems. Yes, you can filtrate. You can use a filtration of this problem, and you can come up with some. You can start with a smaller graded piece. And I mean, there are more. There are things related to foundations. I mean, foundations of this refined Thomas invariants. I think it's still not. They're not. Kontsevich and Soderman haven't completely solved the problem. So there is work to be done there, which is something that I can't say much. I don't really understand the motivic integration story, but there is something to be done there for sure. And there are many things that are, that you can address before you really try to construct such a complicated thing. So.
Any other comments or questions? If not, let's thanks.
Thank you.